is lesson 7.18. In this lesson, we're going to start talking about monomials. A monomial is a number. Let's see, there we go. I can see it. A number, a variable, or the product of a number and one or more variables with a whole number exponents. When we're talking about the degree of a monomial, this is the sum of the exponents of the variables in the monomial. The degree of a non-zero constant term is 0. The constant 0 does not have a degree. So when we're looking up here, in order for it to be a monomial, we can have a number, a variable, or the product of a number and one or more variables. Now remember, product means multiplication. So when we're looking at this, it's either a number, a variable, or a product of a number and a variable. So if you look down here at these examples, we got just our number, we got our number and a variable, so those are multiplied. This one we have our coefficient or a number multiplied by two variables, and then down here we've got a number and a variable as well. But they give you an example as a negative number so that you know that, hey, also it could be negative coefficients as well. Then when we're talking about the degree is the sum of the exponents. Okay, so the degree is the sum of the exponents. I guess I should underline monomials, we know the purple is for that, right? Okay, so when I'm looking at these, this is a plain old number. Remember, it says that the constant, a non-zero constant, the degree is 0. For this one, the constant has a degree, or has a coefficient. Okay, let me try again. The constant has a degree of 0, but the variable x has a degree of 1, because remember that invisible exponent of 1 that lazy mathematicians don't write down. So because of that, the degree of this entire monomial is 1. Here, the coefficient has 0, a has 1, b has 2, so we do 1 plus 2 to get 3. Here we've got 0 for this coefficient, and then we have 5 for the m, so 0 plus 5 gives us a degree of 5 over here. And then this table over here also gives you some non-examples to take a look at. So here we're adding, that doesn't work. We're dividing, that doesn't work. This one, it's raised to a power, so it's a constant and a variable, but it's raised to a power, so that doesn't work. And then this one, we have a variable, but the variable must have a whole number exponent, so that has a negative exponent, so that one doesn't work. So let's take a look down here. We're trying to find out what's the degree of each monomial. So for this one, we have 5 is a degree of 0 plus x with a degree of 2. So our final answer for that one would be 2 for the degree. Here we've got 0 for the 8, 3 for x, and 3 for y. So we end up with 6. And with this one, we've got 0 for that constant right there. So the degree is 0 because there's no variables with it. Of our polynomial is 5. And we're also going to talk about something called polynomials. And a polynomial is a monomial. A lot of nomials here, right? So it's a monomial or a sum of monomials. So polynomial is a monomial or sum of monomials. Each monomial, so just like up here, this is a monomial. Each one of those is called a term of your polynomial. A polynomial with 2 terms is a binomial, and a polynomial with 3 terms is a trinomial. And then here's a couple of examples down here to show you just some examples. Here's a binomial, a trinomial. We also have degrees when we're talking about a polynomial, but the difference between polynomial and monomial for the degree is this one is simply based on the greatest degree of its terms. So the degree of a polynomial is the greatest degree of its terms. So if I'm looking at them and I say, so down here, for example, this has 0, 3, so together that would be 3, this is 2, this is 1, this is 0. So the greatest degree we have is the 3. So that would be our degree of our polynomial. A polynomial in one variable is in standard form when the exponents of the terms decrease from left to right. So, well, those ones were the same. If I had, let's say I had this x squared and this y to the third. So it says that they decrease from left to right. So if I have y to the third and then x squared, so that would decrease from left to right. When you write a polynomial in standard form, the coefficient of the first term is the leading coefficient. So we're writing these in order from the greatest degree to the least degree. And the number right in front of that greatest is your leading coefficient. So the greatest degree for here was 3, and our leading coefficient would be that 2 that's attached right in front there. So let's take a look at how we would do this. So for example 2, it says write 15 minus x to the third plus 3 in standard form, and we're going to identify the degree and the leading coefficient of the polynomial. So the first thing I have to look at is which of these things has the greatest degree. So this one would be a degree of 1, this would be a degree of 3, and this would be a degree of 0. So when I look at that, I want to make sure that I am listing the greatest degree first, but also see what is in front of that term. So notice how that is negative x to the third power or minus. So I have to make sure that I include the sign in front of each term, the appropriate sign, when I'm rearranging the order. Okay, so for example 2, our first term was negative x to the third, followed by my next term, which is 15x, and it was positive, so plus 15x, and then followed by plus 3, which is our last term. So this is now in standard form. So let's just label that here for ourselves as a reminder. And then it asks us to tell us, or to say, what is the degree of this? So the degree for this, remember we're looking at the greatest degree of our terms. So the greatest degree would be the 3, so the degree of this would be 3. And then it also asks, what's the leading coefficient? Well, when I'm looking for the leading coefficient, again, I'm looking for that number out in front of the variable, that first variable. But notice how we just have a negative sign. So there's those lazy mathematicians again. If they don't have to write it, then they're not going to. So this technically has a negative 1 in front there. So our leading coefficient would be negative 1. And you don't have to write that 1 in there when you're writing it yourself. But sometimes we forget that that negative sign means negative 1. So if it helps you to write it in when you're having to identify that leading coefficient, feel free to do that. All right, so for example 3, it says write each polynomial in standard form, identify the degree, and then classify each polynomial by the number of terms. So just trying to figure out, is it monomial, trinomial, or binomial? So when I'm looking at this, if I want to write it in standard form, I write it from greatest to least. This one only has 1 term here, so negative 3 z to the 4th power. If we look at that, so negative 3, that constant has a degree of 0, z has a degree of 4, so when we add 0 plus 4, we get a degree of 4. And then since there's only one term, we would call this a monomial. All right, for the second one, we're going to look at this. We're going to say, okay, well, which one has the greatest degree? So I've got 0 here. 0 plus 2 is 2. And then I've got 1. So my greatest would be 5x squared. And notice it's positive. So I'm going to start with 5x squared. And the next highest would be x to the first, or just x, so minus x. And then this positive 4 with a degree of 0. The degree of this one, since we have a degree of 2 here in the front, that's the highest, we're going to have a degree of 2. And then there are 1, 2, 3 terms. So this is a trinomial. And last but not least, oh, this did not print on here. This is supposed to be q to the 5th power here. So take a second, go ahead and add that in here. All right, so when we're looking at our degrees, we have 0 and 1. So this is a degree of 1, and we've got 5 here. So that would be our greatest degree. So we're going to write that first, q to the 5th, followed by 8q, so plus 8q, since it was positive. 5 is the greatest degree, so our degree of our polynomial is 5. And there are 2 terms, so specifically this is referred to as a binomial. This is lesson 7.1b. In this lesson, we're going to continue talking about polynomials. And if we're looking at polynomials, and we're talking about whether they're closed or they're not closed, a set of numbers is closed under an operation when the operation performed on any 2 numbers in the set results in a number that is also in the set. So for example, the set of polynomials is closed under addition and subtraction, so the sum or difference of any 2 polynomials is also a polynomial. So basically, if I'm adding 2 polynomials together, I'm also going to get a polynomial as my answer. And so because of that, then we would consider this closed. We're actually going to take that idea, we're going to add these 2 polynomials here in example 1a. We're going to find the sum of these. So we have example 1a. Now, we're going to start by stacking these, kind of the way that you traditionally saw them when you were younger and first learning about addition. So we're going to have the first set of polynomial, I guess it's a trinomial here, 2x to the 3rd minus 5x squared plus x. Now, the second one that we had that we were adding is 2x squared plus x to the 3rd minus 1. So we are going to line up the things that are the same. So remember back when we were learning about solving equations, if we have like terms, we got to put those together. So x squared, x to the 3rd power, these are the same types of numbers. So this is also x to the 3rd, that goes here. And then we had 2x squared. Notice that the 2x squared was positive, so I'm going to go ahead and just write plus 2x squared. Then I don't have any plain old x's. See how this one has just a plain old x? But I do have this minus 1, so I need to include that. But I'm not going to stack it under x because those are not like terms. Instead, I'm going to add another column off to the side here. Minus 1, because notice it was minus in front of there, so I have to make sure I keep that sign the same. So now I'm going to go ahead and add what I've got. So 2x to the 3rd plus another x to the 3rd. Remember, this is kind of like having a coefficient of 1 in front of here. So when I add those together, I get 3x to the 3rd power. I have negative 5x squared plus 2x squared. So negative 5 plus 2 gives us negative 3x squared. There's no other x's to add, so I'm basically just rewriting that plus x. There's nothing else to combine with this negative 1, so I'm just going to rewrite that as well. So this would be my final answer, 3x to the 3rd minus 3x squared plus x minus 1. Now, another way that people sometimes do it is writing it horizontally. So it's our vertical method, and we're going to also try it horizontally. So for this one, we had 3x squared plus x minus 6. That was all as one trinomial, plus x squared plus 4x plus 10. So what I want to do here is I want to identify, kind of like here where we stacked the like terms, I want to look here and identify the things that we would consider like terms. So I have a 3x squared. Do I have any other x squareds? Oh, I do right here, x squared. So those will go together. 3x squared plus x squared. I'm going to put them in their own parentheses so I know that those are my like terms together. Then I have, this one is just a plain old x, so I'm going to just change the shape. Even though I'm using different colors, I'm going to change the shape. I also have a plain old x here, and by plain old x, I mean it doesn't have the exponent listed, so it's x to the 1st power. So I have 4x plus x, and again, we're going to put those together in their parentheses, and I'm adding these 2 things together because this is all addition, right? Plus, it looks like I have another set of numbers. Now notice this here is negative 6 or minus 6, and over here we've got our plus 10, so we've got negative 6 plus 10, and again, in our own parentheses, just to kind of combine them together. After we combine them, those parentheses aren't needed. And some people like to write them without at the very beginning. That's okay too, it's all addition. So 3x squared plus x squared gives us 4x squared plus 4x plus 1x is 5x. And then negative 6 plus 10 is positive 4. So 4x squared plus 5x plus 4 would be our final answer for that one. For example 2, we're going to find the difference here. Now, what you need to remember is that it says minus in front of parentheses. So it's kind of like making sure we do the distributive property with that. So let's set it up first. And I like to do the subtraction ones as a vertical problem. It does make life a lot easier when we're trying to see what do we have, where is it going, so that we can do that. So I'm going to start with the first polynomial that was listed. It was 4n to the 2nd, or n squared, plus 5. Now, I'm actually going to take a look at this. So I have a 2n here in my second polynomial and a plain old 4. So I know that I'm going to leave a space for that 2n, and I do that because I do like to list them in their same order. So I'm going to leave a space here and do my plus 5 off to the side a little bit more. Then I have my subtraction, and I'm subtracting 2n squared, negative 2n squared, And then we've got our plus 2n and our minus 4. Now, this was subtraction, right? So I'm subtracting, but that means I have to distribute this negative sign to everything inside. It's kind of like saying negative 1 times negative 2n squared, negative 1 times negative 2n, negative 1 times negative 4. So let's go ahead and simplify that first. So our 4n squared is still there. Our little arrow here. So 4n squared. Negative 1 times negative 2n squared is positive 2n squared. Negative 1 times positive 2n is negative 2n. We had our plus 5 up here. Negative 1 times negative 4 is positive 4. Now, since I've distributed that subtraction sign to everything inside those parentheses, that now makes this problem as if it is addition, right? Because subtracting a negative is the same as adding positive. So we distributed our negative to everything, so we've already taken care of that piece. So we've got 4n squared plus 2n squared gives us 6n squared. There's nothing to combine with this negative 2n, so we'll just rewrite it as negative 2n. 5 plus 4 gives us 9. So 6n squared minus 2n plus 9 would be our final answer. Final answer. All right, let's take a look at example 3. It says a red water balloon is thrown straight down from a height of 200 feet. At the same time, a blue water balloon is dropped from a height of 100 feet. The polynomials represent the heights in feet of the balloons after t seconds. So if you're looking at this drawing, this top dot here, there's our water balloon that's red. I used a pink color, but you get the idea. And this one down here, that's our blue one. Okay. So it says for part A, write a polynomial that represents the distance between the water balloons after t seconds. So what I'm looking at is taking the information that I was given here, and I have to find the distance between them, right? So if I find the distance between, we're subtracting. So that gives us negative 16t squared minus 40t plus 200. And we're subtracting this negative 16t squared. This one doesn't have a plain old t, or t to the first. So then I'm going to put my plus 100 on this end over here. This was subtraction. So let's simplify it for ourselves. Remember, again, we have to distribute this negative sign to everything inside. So we just have two things this time. So we've got the top was the same, negative 16t squared minus 40t plus 200. And then negative 1 times negative 16t squared is positive 16t squared. Negative 1 times positive 100 is negative 100. And we're going to add these things together. So negative 16t squared plus 16t squared. Hey, look at that. That makes 0. Nothing to combine with this negative 40t, so we're going to bring that down. And then 200 minus 100 gives us positive 100. So the polynomial that represents the distance between them, that's this right here. I should label this was part A. So there's our polynomial that we're working with. And what that stands for is the distance between those water balloons after t seconds. So if we figured out how many seconds we wanted to plug in, we could plug it in for t, and we could figure out what's the distance between these balloons. That's what that represents. Part B says interpret any coefficients and constants of the polynomial in part A. So what we want to look at here is what do these things mean, right? So I'm going to actually switch over to my notebook for this part of it. So we're going to call this example 3. That way we have a little bit more space to write. So the polynomial that we were working with is negative 40t plus 100. So if I want to know what that 100 stands for, I really want to look at it without this negative 40t. Well, how would I get rid of negative 40t? I plug in 0 for t. So negative 40 times 0. In other words, after 0 seconds, right? So negative 40 times 0 is 0. 0 plus 100 equals 100 feet. So after 0 seconds, when both of these water balloons are beginning to fall, the space between them is 100 feet. That's what that constant of 100 means for this question, for this polynomial. So the distance between balloons when they begin to fall. That's what that means right there. There we go. All right, and we also have to think about the coefficient, that negative 40. We're trying to figure out, well, what does that mean? So if we think about it, kind of in terms of, think about like when we had slope, right, in previous lessons. As t is increasing by 1 second, what's happening to those water balloons? Well, that means that the water balloons are getting 40 feet closer to one another every single second. So that negative 40, let's use a color just to emphasize the negative 40. Negative 40 represents the amount, the distance between the balloons changes each second. So think about this one in terms of like the slope, right? So every time t increases by 1 second, the distance between the water balloons decreases by 40 feet.
This is lesson 7.2a. In this lesson, we're going to continue talking about polynomials, specifically about multiplying and dividing. So if we look at this, the product of two polynomials is always a polynomial. And for that reason, we can say that the set of polynomials is closed under multiplication. And specifically, we can use the distributive property to multiply these polynomials. So something that we've done in the past that we can relate to this new topic. So if we're looking at example 1, it says find the product. So let's rewrite this onto our notebook sheet. So we got example 1, 3x squared times the quantity 5x squared minus 2x plus 6. Now what that means is that I have to multiply this entire piece here. So all of this, I have to multiply it by each term inside the parentheses. So what we have when we do that, that gives us 3x squared times 5x squared. And then we have, it's a new term, right? So we have our negative from there. So negative 2 times, negative 2x times 3x squared. Now remember, order of multiplication doesn't matter. And the reason that I flip-flopped these is so that you understand that that negative sign came from this 2x. If you wanted to write it as plus 3x squared times negative 2x, that's okay too. I just did it to make it a little bit easier when we simplify. And then we have plus 3x squared times 6. Now, when I go to multiply these pieces, I like to regroup the things that match. So, for example, 3 and 5. So 3 times 5 times, we also had x squared and x squared here. Then here, I've got a negative 2 and a positive 3. So minus 2 times 3. And then I have an x and an x squared plus a 3 and a 6, so 3 times 6 times that x squared that's still there. So now that I've regrouped them, it makes it a little bit easier to simplify. So 3 times 5 gives me 15. X squared times x squared, I keep the base, add the exponent, so that becomes 15x to the 4th. Negative 2 times positive 3 is negative 6. X to the 1st times x squared, I keep the base, add the exponent, so 1 plus 2 is 3. 3 times 6 is 18. And this one I just have x squared, so I'm going to continue to write that on there. So our final answer for this one is 15x to the 4th minus 6x to the 3rd plus 18x squared. Now, example 2, we have 2 different problems that we're going to go ahead and solve here. So we're going to do part A first. So example 2, part A. We have x to the 4th plus 4x to the 3rd plus 11x squared, all divided by x squared. Now, remember when we were solving equations earlier in the year and we had to divide an entire side by a number or a variable. And I said, hey, remember to divide each term by that number or that variable, because then you can see more clearly when you go to simplify. We're going to take that idea right now and we're going to divide each term by this x squared right here. So I have x to the 4th divided by x squared plus 4x to the 3rd divided by x squared plus 11x squared divided by x squared. So each term, see it's separated by the addition here, each term gets divided by that x squared. And that's going to make it a little bit easier when we go to simplify. So here I've got 4x's multiplied on the top divided by 2x's on the bottom. So I keep the base and I subtract the exponents. 4 minus 2 gives me 2. So now we have x squared. In the next term, it's 4 divided by 1, right? Because the coefficient of x squared is 1. 4 divided by 1 is 4. So we've got plus 4. X to the third divided by x squared. 3 minus 2 gives us 1. So now this is 4x. Plus 11 divided by 1 is still 11. X squared divided by x squared cancels out because 2 minus 2 is 0. X to the 0 is just 1. So 11 times 1 is 1. So that leaves us with a final answer of x squared plus 4x plus 11. Now for part B, it's a little bit different when we go to solve this one. So we have 6y minus 30 divided by y minus 5. So when I look at this, I kind of recognize when I look at 6y minus 30, I realize that I actually could rewrite this if I divided each of these terms on top by 6. Then I would have a 6 outside of my parentheses. It's like reversing our distributive property, right? So 6y divided by 6 is just y. Negative 30 divided by 6 is just 5. So if I redistributed, 6 times y would be 6y, 6 times negative 5 would be negative 30. And then I'm going to divide by y minus 5. And now I bet you can recognize probably why I did that, because it's going to make simplifying a little bit easier. Because I notice y divided by y, those cancel out to make 1. Negative 5 divided by negative 5, those cancel out to make 1. So that leaves me with 6 over 1, which is just 6 for my final answer. Now for example 3, when we're looking at this, so we've got 2 sets. So up here we were multiplying, a monomial by a trinomial. Down here we have 2 binomials that we're going to be multiplying. So we're going to be using the distributive property in just a little bit different way. So this is example 3. We have x plus 2 times x plus 5. Now, at the top, we took a monomial and we multiplied it by each piece within the parentheses. So what we have to do here is each term in this first binomial has to get multiplied by each term in the second binomial. So what I want to do is just rewrite everything from that first binomial, so everything in here, and I'm going to separate it and multiply it by the second one. So this would be x times all of here, x plus 5. And then we have plus, right, because it's separated by addition here, that 2 times all of the second binomial, x plus 5. And now I can distribute. So x times x and x times 5. Well, x times x is x squared. X times 5 is 5x, so plus 5x. Plus, now I'm going to distribute on this one. 2 times x and 2 times 5. So 2 times x is 2x. 2 times 5 is 10. Now I look for like terms. So when I'm looking at these, I've got 5x and 2x are both, they have that variable that's raised to the same power. So those are my like terms. X squared is still x squared. Plus 5x's plus 2x's is 7x's. And then 10 was alone as well. So x squared plus 7x plus 10 plus 10 is our final answer for that one. But we also have another method that we can use for solving these binomial products, or polynomial products rather. So we have 2x minus 3 times x plus 5. Now I want to rewrite this first one a little bit, because remember with this subtraction, that really looks like 2x, and then it's like plus -3, right? I'm going to put brackets around that so we can kind of decipher the two. And then x plus 5 was still x plus 5. So what I'm going to do is I'm going to use kind of like an area model that you've learned in previous grades for multiplying these. But I split it into my two terms that I have here. So I have from our first one, let's go ahead and color coordinate these. So we've got 2x and -3 here. So 2x and -3, or -3. And then my second one, I had x plus 5. So we're going to do our x, and since it's positive, we're just going to write that 5 there. So now, just like when you use a multiplication table, we're going to multiply this column by this row. So 2x times x. Well, that would give us 2x squared. And then I have -3 times x. So that's -3x. 2x times 5, so that gives me 10x. -3 times +5 is -15. And then from here, I take the pieces that are in the boxes and I write them as an addition problem. So let's kind of scoot to our notebook here. So example 4, that left us with 2x squared minus 3x plus 10x minus 15. So writing all those terms, see, I got them from the boxes. I just wrote them on here. And then just like in the previous question, we want to look for like terms. So I have an x to the first, x to the first. There are my like terms here in the middle. So to simplify, 2x squared, that stays. -3x plus 10x is 7x. And then that minus 15 also doesn't have a partner. So 2x squared plus 7x minus 15 is our final answer using that area model. This is lesson 7.2b. We're going to continue talking about multiplying polynomials together. One of the methods that we're going to talk about today is the FOIL method. And the FOIL method is a shortcut for multiplying two binomials. So if you take a look at this, so it says to multiply two binomials using the FOIL method, you're going to